Good afternoon, everybody. Welcome to today's TSVP talk. It's my great pleasure to introduce today's speaker, Professor Paolo Salani. Paolo is a full professor of mathematical analysis at the Department of Mathematics and Computer Science of the University of Florence. And he is also the vice president of the Italian Mathematical Union, as well as the director of CIME Foundation. So he works on isoperimetric and other geometric analytic inequalities and geometric properties of solutions to elliptic and parabolic PDEs. Today, he will talk about isoperimetric inequality. Please.
Thank you to OIST for giving me this opportunity to be here. It's really an amazing place. So I hope I'm not going to annoy you too much because mathematics is not easy sometimes to present to a general public. So let's start with some picture. So look at this picture of baby animals. So and think to their parents, and think if you see any common geometric quality, the shapes of this baby, especially with respect to their parents. So, by the way, this is one of my boards. So, I don't know. Do you see any? Do you think that there is some geometric properties that these baby animals have with respect to their parents? So I don't know. This is my impression. This is not something scientific, but my impression is that they all are more round-shaped than their parents. Do you agree? So, and indeed, also, if you look to anime or manga, when you want to convey the idea of childhood, usually the artist just make them more round. You think about usually, so if you see something which is more round and similar to something, but so it means that it's a baby. So that we have this impression. So I don't know. This is just my. Don't pretend to be that this is completely true, but this is my impression really. And so then, in such a case, there is a possible mathematical explanation behind this, which is the isoperimetric inequality. So the subject of this talk. So what is the isoperimetric inequality? So the plane. So it is very simple. It says that among planar sets, all the possible sets, really all the possible, but then I will say something later. So among all the possible sets in R2 with a given perimeter, so the disk is the one which has the largest area. So you have fixed the perimeter. So I think you have a rope. You want to dispose this in such a way to surround the biggest possible set. The rope is fixed. So, yeah. So if you like, then if you put this like a circle, then you have the disk inside, and this is the maximum of area that you can surround. Equivalently, if you fix the area, then the disk has the minimum perimeter. Okay, and you can also express this with this inequality. So 4 times pi times the area of any sets in the plane is always less or equal than its perimeter square. Okay. And for mathematicians, the equality case is particularly interesting. So equality holds if and only if the set is a disk up to something. But essentially, the class of sets that you like, this happens only in this case. So we have competitors, and the winner is the disk. Okay. So the same happens in R3, the space. So you think to sets which have the same, they all have the same surface, the same perimeter, the same measure of the perimeter, which means the same measure of the surface surrounding the set. Then the ball is the one with the largest volume, or equivalently, if you fix the volume, then the ball has the smallest perimeter. You can also express with this quantity. And And this is true in Rn for every dimension, not just in the ball, not just in the space, not just in the plane, just in the space, in Rn. So whatever dimension you choose, the ball is the best set if you fix the perimeter. Maximal measure is one. So let's go back to why possibly my impression is true. Why maybe? So a newborn is a baby animal. Human baby is particularly weak, vulnerable. So the first stage of our lives, so the protect us from the danger is the most important thing. So, and where the danger are coming from? So mostly from the outside, So you have to protect from possible injuries that are coming from outside. And so the less perimeter you have, the better it is. Moreover, not only dangers, but also there is this change of temperature of heat from our body to the outside. So if you have so you have to contain this volume because you need the organ, you need some time. So you cannot be too small, but you need to have a volume, but you prefer to have less perimeter because so you are more protected. Think to a nation that luckily now we are again speaking of wars. So nation has to protect the boundaries. So the best boundary, simplest it is. Play it physical, you know that best boundary, it's easier to protect the territory. And so, okay. So this is probably the explanation why all these babies look more. So, you know, in general, nature always aims to minimize some kind of energy. And it is to always want to optimize the resources, something that sometimes we forget to do. Okay, but this is not the only consequence of the isoperimetric inequality. For instance, it explains why planets and stars are almost round-shaped, or why the kettle, my home, is this shape. So of course, a ball would be more efficient, but then you couldn't put on the fire. So, or why the soap bubble are spherical. There is a lot of mathematics around this, not just isoperimetric. A lot of mathematics. And also why the sphere has the smallest electrostatic capacity among surfaces enclosed in the same volume, or why if you take a bar, you give the area of the section, then what is the strongest, the one, how do you have to take the section to have that this bar is more can resist better to torsion? Then again, the disk is the solution. Okay, and many other. I could give many other examples, but let me stop and let me write. So, what is the isoperimetric inequality in general? So, in general, in Rn, you can write the isoperimetric inequality this way. So, you have a set. This symbol, this means that you take the measure of the set. Okay, so in Rn, you can define some measure in the space. It is the volume. In the plane is the area, and here there is the measure of the boundary of the set. These two measures are different. So the set is n-dimensional. The space, the set is three-dimensional, while the surface is something which is two-dimensional. You have like a paper, a sheet of paper that you want to arrange. And in the plane, the set is two-dimensional. There is area, but the boundary is one-dimensional, is a curve, the rope that you want to align. So, but so this symbol is the correct measure for both. And then you have that the volume raised to power n-1, which is the dimension of the boundary, times some constant. This constant is the correct one to have equality when it is the ball, precisely. It is omega n just means the measure of the unit ball. Then think to in the case, the plane here, n is 2. In the case of the space, the n is 3. Then here you have the measure of the boundary raised to power n, which is the dimension of the set A of the volume. So if you So these exponents are the right ones, so that if you delete, of course, if you translate the set, nothing happens. So everything remains the same. And if you delete the set, then the deletion of a set, if you take twice the set, then the volume or measure becomes 2 to power n, the original volume, while the measure of the boundary becomes 2 to power n minus 1. So the 2 to power n times n minus 1 in both sides cancel. So this inequality is insensitive to the deletion and translation. Okay, we say that it is sensitive to homotopy. So, okay, so you can delete, and it will always remain the same. So you can fix the volume of like 1 or whatever, okay, or fix the measure of the boundary. Is the same. So, and the quality conditions are important. The quality only happens if and only if A is a ball up to negligible sets. For instance, if you take, you just add the point somewhere, happens. It has no measure, the point. If you are in R3, the point has no measure, and also its boundary, just 1 point, there's no measure, so it's to subtract 1 point, so on. Okay. So, so on the other hand, this easy statement, which is quite clear. So the ball is the best. Everybody could guess this probably, but this naive statement hides many difficulties. In particular, what is the measure of a set? What is the measure of its boundary? So if you have to tell me the area of a rectangle, it's very easy. The base times the height. If you have to tell me the area of a triangle, there is a formula, okay? But generally, if I take a set made sorry, it's not made in this way. So what is the area? What is the length? So there is behind a lot of things about defining properly the measure, defining properly the measure of the boundary. So, and indeed, the solution, although despite the solution was already known by ancient Greeks and Roma, so very, very long time ago. So to find a complete sound proof required a lot of time, thousands of years. So it's quite recent, the complete proof of the isoperimetric. So let me give a little bit of history. So it's everybody, so it's generally, we believe that, so mathematics was born because there were some special need. You have to count the ships that you are taking back home, or you have to pay something, you have to count the pieces that you are giving to another person, or you have to divide some piece of land in a fair way between the people, or you want to buy a piece of land for someone else, and then you have to pay something. How do you decide the price? It depends on how large is the land. How can you measure how large it is? So the very beginning, so the first naive idea was to, yeah, I can just measure boundary, and then I can have an idea of how large is the land. So I can measure easily. I have just to walk around, count the steps that I have to do. So it's very easy. But this idea is not good, because you can easily construct some set which has almost zero area and almost infinite boundary. So you can take just a rectangle which has a very, very small height, a very, very long base. So the area, you can make this like n, and is a natural number, and the height 1 over n squared, and then the area is 1 over n. Then you take n very, very big, and so the area becomes very small, but the perimeter is going to plus infinity. Okay, so it's becoming very, very large. So this is not a good idea. So it depends on the shape that you are giving to your land. So the shape is very important. So a classical, practical optimization problem is this one. Assume you have a 100 meters of fence or a rope, or whatever you like. So what is the maximum area you can enclose, and what shape should you give to the fence? Then this is precisely the isoperimetric problem. And Archimedes was probably one of the first to study this problem, and he has the first ideas and gives some contribution about it. And it seems that he knew the solution was the disk. So 3,000 years ago, something like this, or almost. So, and about this, there is particularly interesting, the legend of Queen Dido, so which was also told in the Aeneid, which is a famous Latin poem by Virgil. And, so what is this legend? So Queen Dido was the founder of Carthage. Carthage. Okay. So, and she was the first queen, of course, because she was the founder, around 800 years before Christ. So much before the Rome, something that Rome always like, oh, come on, they are older than us. So indeed, Virgil put this story in his poem just to make a connection between Dido and Rome, between Carthage and Rome, so say so, but I don't want to speak about this. So what happened? So she was living in Phoenicia, in Tyre, okay, which was her hometown. She was the daughter of the king. The king died. There was also a brother. The brother was Pygmalion, and he became king. But he was jealous of Dido and her husband. He was afraid that she, together with her husband Sichaeus, could pretend to have some power. So he killed her husband. He murdered her husband. She knew this, and then she escaped together with some loyalists, some other people, and then they went away by boat. And after a long journey, they landed on the coast of North Africa, now in Tunisia now. And there she went to the local king, Yarba, and she asked for some land to settle down there, to make a new city. Okay, Yarba says, the king says, okay, you can have some land, but then he gave her a bull skin, and he told her, then you can take as much as land that you can surround, you can take with this skin. But he couldn't believe that she was so smart. What she did was to cut the skin in very tiny strips that were tied together, and then she made a very, very long rope. And then what she did, she take the sea, around the sea, and she disposed the rope in such a way to take the maximum volume, maximum area. And by the way, there was also a hill here in the middle, which was very particularly good to make a city. And then she pretended to have all this land, and the Yarba was obliged to give this land, so she could found Carthage here. So it seems that she knew the solution of so this is a legend, of course, but so it seems that she knew the solution of the isoperimetric problem. This is called the Dido problem. So now here you don't have the whole space, but you can use half plane. You can use this line. So the solution then was known more than 2,000 years ago, or maybe even 3,000 years ago. And for the planar case, then, so what about the proof? So one thing is to know the solution. Another thing is to know that it is really a solution, to have a proof. So Zenodorus proved that if you take any regular polygon, then the disk is better, this point of view, any regular polygon with a fixed perimeter. And but if you consider all possible set, not just polygon, regular polygon, then it took a long time before Steiner gave the first important contribution around the beginning of the 19th century, and which was made by Steiner symmetrization, which is something which is still very useful. So essentially, you take a set like this, then you cut in one direction, and then you take this and you put here in such a way that it is, then you get a set which is symmetric with respect to this line. And what happens is that the perimeter is diminished, but the area is remaining the same. Then you can make, at every step, you can make the set more symmetric, and you are going towards a better situation from the isoperimetric point of view. So unluckily, his proof had a problem. for the gap. So of course, then you repeat this procedure for every direction, you arrive to the ball. So the ball, so the disk. So the disk is the solution, but there is a gap. So everything works perfectly. If you have a solution, but it didn't prove that a solution must exist. And this gap was remedied by Blaske some years later, who proved that a minimizer actually exists among all planar convex sets with given perimeter. So, okay, but why it is so important to prove that a maximum exists? So he proved that you go towards the ball is better. Yes, if a solution exists, but if a solution doesn't exist, maybe you are saying something very stupid. Look to this. So if you take a problem and something that you really know that it is stupid, that it is wrong, but you assume that a solution exists, you can prove something very stupid. Take the natural numbers, 1, 2, 3, and so on, okay? And so let us prove that the 1 is the maximum of the natural number. The maximum, not the minimum. Of course, it is the minimum, not the maximum. Okay, look at this proof. So assume a maximum exists. Then let us consider any natural number, n, which is not 1. You take n different than 1. Then can it be the maximum? No, because maximum means that there is no number greater than e. Okay, you take n squared, and the square is greater than n, so n cannot be the maximum. Then if a maximum exists, since it cannot be any number different from 1, then it must be 1. So what's wrong? So this is perfect. This argument is good. There is no wrong, no mistake in this argument. The mistake is in the beginning. There is no maximum. So you cannot just prove that the maximum is this way if you don't know that the maximum exists. Okay. So far we arrived to a proof in R2 and then more time to have a proof in Rn. So let me recall just Ennio De Giorgi and Renato Caccioppoli, two very important Italian mathematicians. Probably Ennio De Giorgi was the strongest Italian mathematician in the 20th century. And he finally gave a proof for every dimension around the 50s using some ideas also. Okay, but why should we bother at all about a proof if we know the solution? Come on, if you are an engineer, you don't care about the proof. I know how to do this thing. I don't know why you could prove it. Yes, but without a proof, sometimes our intuition gives us a bad answer. And so if you believe something which is wrong, it can be very dangerous. In practice, I mean, not just from the mathematical point of view, not just I publish a paper which is wrong, something which is really dangerous. And now I'll show you an example. If I ask you for a planar set which is always the same width in every direction, I mean the width, okay, I take a direction, for instance, this set, and just I take two sets which are opposing it, and I measure the distance. This is the width, and I do this in every direction. Then if I ask you for a set which is always the same width in every direction, which is equivalent that you put the two lines and you can roll the set inside and it is always touching. So you probably tell me the disk, okay? So this is, so assume that, okay, disk of course has always the same. It is equivalent if you just, okay. Roll it between them, it's always touching, okay? You say, probably think about, do you have any other idea? There is any other set? Probably think it's very hard, probably. But this is not true. So, for instance, the Rayleigh triangle. What is the Rayleigh triangle? The Rayleigh triangle is this red set, which you can construct in this way. You take just an isoperimetric triangle, then this is an arc of a circle, which has the ray like this. The radius is like the side. You point. You have the centrum here. The center is here. You take this radius and you make this arc of circle. You repeat the procedure for every side and every vertex, and you get this set, which is called the Rayleigh triangle. Well, the real triangle has always the same, every direction, it has the same width. It's constant width, like the circle. You can roll it. You can make a bicycle with the wheels made in this way. It is going perfectly horizontal to the plane. Maybe you go this way, but you are going perfectly horizontal. Okay. So, and you can use this to make a square hole in the. So if you start to rotate this, you can make a square hole with a drill. So this is a very interesting set. And okay, and it is not the only one set apart from circle which has this constant width. There are infinitely many. There are some points made in this way so that you can use in the machine and you can save some metal. And so let me say, so, okay, as I told you before, if you are in the plane, you can take something. So the area can go to 0 and the perimeter can go to infinity, okay? But if you look just only to the set with constant width, then you can prove some inverse isoperimetric inequality. So you can find a set which has the minimum area. One, you fix the width, which means you fix the perimeter, which is precisely the real triangle. Okay, the real triangle minimizes the area among all sets with constant given width. And in R3, the same problem is open. So if you are interested, there are some students, you can try to prove in R3. So the only contribution, essentially, the main contribution is this paper by 3 colleagues of mine. So they proved that among all sets with constant width, which are obtained as a rotation of a 2-dimensional set, so you rotate the real triangle, you get the minimum, but you are only looking to this set which are obtained in this way. So this is essentially the only contribution. Then the problem is still open. And so let me pick the occasion to remind this colleague, good friend of mine, which Paolo, which was passed away less than years ago. One of the most brilliant person in the world. Okay, so but why did I say that it can be dangerous to have a wrong, so to have a proof? If you don't have a proof, you don't know what you are doing. You think you know the solution, but you don't have a proof. So let me tell you another sad story. Sorry, if the talk is taking this wrong mood. Okay, so this is also another sad story. So probably you don't know, some of you are very young, so you don't even know what is a space shuttle. Space shuttle was a spaceship that in the 80s, so it was an American spaceship. This is a space shuttle. So it could start like usual spaceship, but then it can land like an airplane, so it can come back. And it was made, there were these 2 boosters, the white one, and this fuel, this tank. So the tank was the only things that was destroyed when you start. The booster and the ship, the spaceship, they were coming back to the Earth. So the booster started, and at a certain point, the booster fell down with parachute, and then they were taken away from the ocean and taken back to the NASA place, and okay, and the spaceship went on and then came back. But so there were many missions of this space shuttle, but on January, so but then in the history there were 2 accidents, 2 fatal accidents. Then they stopped. It was also quite expensive that they stopped the program. But so in the first accident happened in 1986, and just 73 seconds after the starts, it exploded, and all the crew died, of course. Among the few, there was one elementary teacher, I don't remember. Yes, it was the elementary teacher. He won a competition to be there. She was the first civilian to do space with this. So there were, so this is explosion. So I can tell you that I was looking on TV, because every time the space shuttle was leaving, then it was showing on this. Was really incredible, something. So, okay, so then there was a presidential commission to understand why this happened. And The commission then determined there were a lot of scientists inside this commission. So you can see this fire here. Then at the end, this is a boost. This is one of the booster. Then it happened that there was this fire coming outside. So this booster was made by several pieces, which then fell down to the ocean, and then they were put again together for the next mission. Okay. So so at a certain point from the booster, instead that just here, this is the correct fire that you should have. There is this fire which hit the tank, and then it's exploded. And the problem was that when you put together these pieces, then there are some O-ring connecting them, and there was a problem, especially this O-ring was made by some material which was not behaving very well to the change of temperatures. But this was not the only problem. Among the members of the commission, there was the Nobel Prize Richard Feynman, and he also told several times, and he also wrote in his personal report and also in his autobiography that there was also one problem, one mathematical problem, that the engineer at NASA believed that the circle, the disk, is the only set which has constant width. And so what they did when they took back these pieces, and they have to put them together before they have to check that they were still shaped. So they put these and they roll them between two, so to be sure that you have they still be circular. Then they put together. So it says this is not a good procedure, because you cannot be sure that it is a circle. So probably if you have a little bit some difference, then you put this together. There is the O-ring. Of course, you can arrange them, but the ring pick them together, but it's not a stable solution. So as you can see, if you don't know what you are doing, if you think to know the solution, but you don't have it, then it's better to think about. Okay, so this, but now, so since I gave you some sad story, then now some fun. Okay, I will give you a proof, which for mathematician is a lot of fun. So as I told you, it is very hard inequalities. It's very hard to prove the isoperimetric inequalities. But then there is this other inequality, the Blooming-Kosk inequality, which is something which I work about also together. And so this inequality is very powerful, in fact. And with this inequality, you can prove the isoperimetric inequality for a very large class of sets. Say very easily. You have just to make one derivative. So first order derivative. So I think, of course, there are some competition, but I hope that everybody can remember about the first derivative of the function of just one variable. Okay. Okay, what is the Blooming-Kosk inequality? So the Blooming-Kosk inequality tells you this. If you take two sets which are measurable, as I told you, to measure some deep plane, you can say what is the area, the space, you can say what is the volume. It makes sense to speak of volume, area. And then you take a combination of them, a convex combination, some mean of them. Now I'll tell you what this means. To make this 1 minus t, think t, you can think t equal 1/2. Then you have k0 plus k1/2. And you take the volume. You raise to power 1 over n. N is the dimension of the space where you are. So if you are in the plane, n is 2. If you are in the space, n is 3. So which is exactly the homogeneity degree of the space. So if I take a set, if I double it, then volume will become 2 raised to power n, the original volume. Okay, so this is important. Not for the proof. Yes, also for the proof. Then you have that this, you can estimate this volume of this combination using the original volume of K0 and K1. It's just the convex combination of the same volume, also raised to power 1 over n. Okay. So, and the quality here can happen if and only if they are the same set And also convex. Convex means that you don't have a situation like this. Convex is something which is more or less round. So means convex set is something that so this is not convex, because for a convex set, every time you take 2 points and you consider the segment joining them, it must stay inside the set. Then this is not convex. So if you want to have this convex, then you have at least to have all this part here. The set, this set is convex. Set is convex, of course. Okay. Convex and so on. As soon as you have some part which is going inside, it is no more convex. So, and they must be also homotechnic. It means that apart from translation and dilation, they must be the same set. So the same shape. Okay. Up to removing something from inside. You cannot add, you can just remove. Okay, something which is like 1 point, something which is. So here again, this is the measure. Okay, what is this addition? It is just the usual addition. You take any points on K0, any points Y on K1, and you just make this addition. So let me show. So another way to express this inequality is to say that the volume raised to power 1 over n is constant, okay, in the class of set. This is not because just let me show you how you can perform this addition. So take a square, take a disk, you make this addition. It means that you take any point here, you see this like a vector, any points here, you see this like a vector, and you make the addition of these 2 vectors, you have these points. And you repeat this for every point here. What you get at the end is this, now I make just 1 plus b, then you can divide it by 2 and you have. And so what you get is this sort of rounded rectangle. Okay, so I didn't make this picture, I took from this paper. So this is the final result. Okay, so it's very simple. You repeat this for every point here and every point here. You can combine a point with any other point here. Another way is to take this ball and to make this go around A or vice versa. You get always the same. Okay. So, okay. So now you know what is this Minkowski addition. And now, so as I told you, the Bloom-Minkowski inequality permits to you to prove the isoperimetric inequality in a very large class of set. Okay. Essentially the set where you can make the perimeter, where the perimeter is like the Minkowski content. What is the Minkowski content? So you can find the perimeter of a set just using the measure, just using the Minkowski addition. So essentially you take the set, you add a ball of radius epsilon b1. B1 is the ball of radius 1. If you multiply by epsilon, you have ball of radius epsilon with epsilon very small. You subtract the volume of A, you divide by epsilon, you take the limits as epsilon tends to 0. Okay. So what is so if you go back to this figure, then you want to find the perimeter of this rectangle. Of course, you can do, but thinks that it is a more complicated figure, more complicated set. Okay. Then you add the ball, and then you take the area of the set that you get, and you subtract the area of A. Then you get the area of this part here. And then you take the ball here. The ball is as radius 1. Then you take the ball smaller and smaller. Then you have something which is smaller and smaller. Okay. Then you have something which is very close here. Then you take this area and you divide it by epsilon. Essentially, if you think the area divided by the area is exact, more or less, it is the perimeter times epsilon. Think to this part here, there are the perimeter times epsilon plus this is the perimeter times epsilon, because You have this times epsilon, you have the area of this, the area of this, the area of this, the area of this, plus there are this part. But this part, when you send epsilon to 0, they are disappearing very fastly. They are going like epsilon square. Then you divide by epsilon, still an epsilon remain, and it's going to 0. Okay. So this is a way to find the perimeter of very complicated features, very complicated sets. So very large class of sets you can really use. Okay. So if you define the perimeter in this way, then the isoperimetric inequality is saying that this Minkowski content is always greater. This is the same, just right, the same inequality I wrote at the beginning, just raise it to power n-1, and then just pull the perimeter with this. Okay. So as I told you, you can fix the volume, the perimeter of the set, then just take all the sets with the same volume of the unit ball in the plane is pi. Okay. Then this simply is read, so this is just Wn to power 1 minus 1 over n, then something cancel, and this is what you have, which is telling you that the perimeter is always greater or equal than the perimeter of the ball. Okay, this is just the perimeter of the ball. Now what you have is that now we have to write down this. Okay, then I take the 1 plus epsilon b1 raised to power over n. I write this in this way, just multiply, divide by 1 minus epsilon. Then now this, we are precisely in the condition of the Bloom-Minkowski inequality. Then this is greater or equal than 1 minus epsilon, the volume of this set, raised to power 1 over n, plus epsilon, the volume of the ball, power 1 over n. But the volume of this set is the volume of A divided by 1 minus epsilon to power n, or the area, if you like. Okay. Then if you write down what you get, it is that this is greater or equal than the area or volume of A raised to power 1 over n plus epsilon, the area or volume of the ball raised to power 1 over n. Now you remember that you take this equal, you call this volume Wn. This is not important how you call it. It's just the volume of the unit ball. Then this is just the volume of the unit ball to power 1 over n times plus 1 epsilon. Okay, and now we go back to write the definition of perimeter. Then this is 1 over n. Then you have to raise to power n, and you get Wn. This is, you know that this is greater or equal than this. Then of course this is greater or equal than omega n times 1 plus epsilon to power n minus the volume of A, which is Wn. Then you can factorize Wn. You have the perimeter is greater or equal than the omega n, sorry, times the limit as epsilon tends to 0 to plus 1 plus epsilon to power n minus 1 divided by epsilon. But if you look to this and you remind the definition of derivative, a one-dimensional function, if you take the function f of x equal x to power n, this is precisely the definition of the derivative of f calculated at 1. This is very easy. It's just n. So what you get is that the perimeter is greater or equal than Wn times n, which is exactly what we wanted. Okay. So that's all. Stop here. Thank you, everybody.
Thank you very much for this great talk. Do we have any questions from the audience? Some questions, but let me ask the first one. So you mentioned this, I mean, I like this elementary proof at the end, but how about, how to prove this Bloom-Minkowski inequality?
Yeah.
That is quite tough.
Yeah, so this proof is easy, but we are using something very powerful, the Bloom-Minkowski inequality. So it took 2,000 years to prove 50,000 years to prove the isoperimetric inequality. Bloom-Minkowski inequality also took 3,000 years. So it's easy. Once you have something very powerful, then you can make some task before was looked impossible, easy. Now you have artificial intelligence, or we have a very powerful, so to make a presentation like this, years ago was very difficult. Now it's easy. Laptop, take it. So we saw a spaceship, probably that they use it to make all the calculation. It's less powerful than. So you have something very. Just
okay. Hello, I have a question.
Maybe could you wait?
Steven, can you hear?
Could you
Oh.
ask a question later? Maybe we have one question from our on-site audience.
So
Oh, sorry.
I wanted to know when did the idea of existence come into mathematics, and when did mathematicians start thinking about existence proofs historically?
Yes, they started to think to existence proof because at the very beginning, everybody was convinced that that proof was perfect. The standard proof. So you take a set, you have a set which is symmetric with respect to one direction, which is better. Then you repeat this for every direction, you arrive to the ball, and the ball is the best. Someone then say, yes, but what about, so someone understood that you need to know that the solution exists. So that was that moment, that period that there was also then the proof of bias trust that you have a continuous minimum, otherwise easily give example of things where think there is a maximum minimum exist. So that was a period of the history of mathematics where some ideas, or probably they didn't, they were just looking to the solution because they believe it exists, but you can understand the proof of the existence.
Yeah, I mean, I understand that, but when do you think that, so for example, the Greeks or the Romans, for example?
No, I don't think. I think it was that period in the 19th century, in the 18th and the 19th. Do you mean this when they started to think that there is this need? I think not an expert in history of mathematics, but I think that was the period between the 18th and the 19th century. They start to understand that you really need a proof. Or people could believe this, especially this proof also be believed. Till one says no, it's problem. That was the period when they started.
Thank you.
Let's welcome the question from the online audience. So if you have questions, could you unmute yourself and ask questions? No?
Me, yes.
Yes, please.
Yeah, again, sorry about before. Like I thought his turn was over, but sometimes we just keep losing the speaker's audio. Yeah, like so many times we lose the
really?
speaker's audio, so I don't know if I can like catch on to it.
But you can hear us now, right?
Yeah, I mean the professor. Yeah, I'm talking about him.
Yeah, yes, I can hear you. Sorry, I
didn't realize.
I couldn't realize that you couldn't hear. Do you hear me now?
Yeah, I can hear you fine now.
Okay, thank you.
Yeah, I mean, I was gonna ask questions about black holes. Yeah, how would this? I'm sure this could apply to black holes.
Oh, black holes?
Yeah, I wonder how this would apply to black holes and
Do you mean the isoperimetric inequality?
parametric inequality. Yeah.
Yes, probably this tells you that black holes must be round shaped, which is something that everybody believes, I think.
Yeah, since it's also spherical. Yeah.
Yes, I think, but So I cannot tell you the details, but I expect that you can use the isoperimetric inequality to prove that the black hole must be circular, spherical. How it cannot be nothing different like a star. Of course, there are, so when you have a star or a planet, there are also some other forces. It is rotating. So at the end, you have to take in account of everything. It is not just that it is the best way, according just to gravity, the sphere is the best way to shape matter. So in the black hole, gravity is essentially the only things that you have to think about. The other forces, maybe there are, but they are nothing, because gravity is going to infinity. Then only gravity counts, and you are only subject to gravity, then you must have a ball. So I think this is a naive explanation, probably. Sorry, I didn't think really about this, but I think this is an explanation tells you that according to the, because the isoperimetric inequality tells you that if you are only subject to the gravity, then you must.
Yeah.
So I hope I answered your question.
And
Thank you.
that's it then.
Thank you.
Yeah, with the infinite gravity. Yeah, that's where
Yes, so I think
that's
it is
where
the
things
only,
get interesting. I mean,
so you have not to take in account of any other influence. Of course, there could be, but at the end, they are not. It's like if you have a planet, then you can think only to gravity. General for a planet, it is not. It is not that there are the gravity also of the other planets. So, of course, in the planets there is gravity, but not only his gravity, its own gravity, but also the gravity of the other set. It is probably rotating. It is probably so there are many things to take in account. For the black hole, in principle, you have all the other things, but they are negligible with respect to the gravity. So you can just think that the black hole is just subject to its own gravity, nothing more. All the rest. I think this. Sorry, this is probably quite naive, quite rough explanation. Almost correct.
Yeah, okay. So my question was regarding the curves of constant width that you spoke about, the rouleau triangle.
Yes.
So for something in the plane, I can see that the requirement is that it it touch two parallel lines.
Yes.
And if you want to generalize it to surfaces, you'd have two parallel planes.
Two parallel planes.
But
yes.
would it be sensible to talk about constant width for space curves, let's say curves in R3? Like how would you define for something that has torsion also?
So you always, so if you have so you mean still in the space, but Gauss space, sorry?
No, normal Euclidean space, but
Okay.
not a plane curve. This is a curve with some torsion.
Okay.
Twisting also involved. So if I want to define, let's say, width for it, how would I go about even defining width for curves in space, in three-dimensional space?
So the only way to define the width is this one. So you take the two hyperplanes and if you touch the same, which are parallel, and you touch the whatever object you have, and then the width in this direction. You're asking for constant width, then you have to make this for every direction. And of course, you can define this for a curve, for whatever you like. You have an object, some set, not necessarily full dimensional. But then what is, so, but the problem in the space is also that, so in the plane, you know that if you take a set which is not convex, so essentially if you make this operation, So you are thinking to a convex set at the end, because you are surrounding always, you make this operation, you have a set, whatever it is, maybe it is not convex, and you start to make this operation, you consider the set that you are surrounding the intersection of all these slab that you create with this parallel hyperplane. What you get is a convex set, which does not coincide in general with your original set. It was not convex. So, but in the plane, if you make this, you start to make this for every direction. At the end, you will get what is called the convex envelope of the set, which is just the smallest convex set, including which include your set. And in the plane, you are sure that the perimeter of this convex set is smaller than the perimeter of your original set, while the area is bigger. Then if you are thinking to this isoperimetric problem, it's sure that you can just forget all the rest and just think to convex sets, because with this operation, you are sure that you think this length is larger than this. Then the perimeter is diminishing, the area is enlarging. So forget all the other set. You can think to convex set. But if you are in the space, this is no more true. Then if you do this operation also for something which is just a card, so you get a convex set containing this. Of course, the volume is bigger, but what about the surface? It may look that the surface is going down, but this is not true. If you just think to something which is made maybe even to disk, and you connect them with some tiny or even strip, and you make this operation, then what you get is this cylinder. Of course, the volume is larger, but the surface of this cylinder can be much bigger than the surface of the original set, because you have all this. This is very big at the end, while this was very tiny. So then you have to control if the volume is enlarged, but also the perimeter is enlarged. So are you really going towards a better situation or not? Then I don't know if I clarified a little bit your question.
My concern was like more about have some three-dimensional space curve.
Yes, some curve, you say.
Yes, that has torsion and all that.
Yeah, with some torsion, I understand. Then you want to make, of course, you can define again, and you have this put in the space. Then you can still define the width of this. If you just think to the width, you can do this. But in this case, this curve has no volume. Then what you would like to say? So maybe you can think to some kind of isoperimetric problem. Then among all the possible curve which are of fixed length in the space, then it is the one that optimize what they are. If you take a soap film, then you can think to this. You put this in the soap, you take it outside, then the soap makes some surface here. Okay. Then the best is if you just take circle, so you have the largest surface. You take this shape instead, then curving this in all these, then you have all these surface, maybe many different kind of surface. Then you can probably some problem like this you can think. So sorry, I wasn't at the beginning. I didn't understand. Sorry, but in the space, of course, also the example that you are asking in the space, you can make much more problems. Also in the original problem, there are more problems, much more. It is much more difficult in any case than the original one. So.
Any further questions?
Thank you very much. I have two questions. If we go back to the proof of the Works now. Okay, so we had this definition of the perimeter in terms of the limit process with this ball. I have two questions concerning that limit. The first one is, what happens if we change the set B1 to any other convex set? Would we get out a perimeter, or what would be the limiting process?
Yes, you get a perimeter, which is called the, so it depends. So you take any convex sets, you can decide that this is the ball of your space. So, and then you get a definition of perimeter, which is anisotropic. We say that it is an anisotropic perimeter because you have a different set. You take this as a ball. Then then it means that if I go in this direction, so maybe I can use more. If I go in this direction or I go in this direction, I take the distance in a different way. This is, say, the unit distance in this direction. This is the unit that you are using in this direction. So then you have you measure the perimeter in a different way. And you get the measure of the, you get the anisotropic perimeter. You can use this definition, give a definition of perimeter with respect to this ball, which coincide with other definition that you can for a different ball also. Coincide as soon as this gives you the perimeter, which is true in a very large class of set. If the set are C1, so, or if they are positive reach, it says, which means that positive reach means that there is at least you stay at least quite close to the set. Then for every point here at distance epsilon, you have only one point on the, there is a one-to-one projection. Then for all these sets, this gives you the correct definition of perimeter, whatever you choose. Also efficiently, yes.
So does that mean that if I change the set B1, that I get an isoperimetric inequality for every type of perimeter, but just with a different constant?
Yes, you have the same, the proof works the same. And but of course you have a different constant, which depends on the sets B1. It is the measure of the B1 that you take here. So you fix this, and then you have that at the end the measure of the sets. The perimeter at the end will be greater or equal than the perimeter of the ball. Yes, it works.
Okay, thank you very much. And my second question would be, so the perimeter here is basically the first derivative of the set A with respect to that measure. What would happen if we take multiple derivatives?
You get what are called mass integrals. So you can expand this volume epsilon up to epsilon n. This is at the end the volume, the measure of this set is a polynomial of P. You have this expansion, and all the coefficient have a geometric. Last is fixed, and it is just the epsilon and the both. Okay. The other one, the first is the perimeter. The second one is something. So they are called mass integrals of the set. Convex geometry, they are very important. The last one before the one with epsilon to n minus 1 is the mean width, which means you take this factor of the width, you make the mean with respect to every direction, then you get the coefficient, one of these coefficients. The other one are something in between, which are the set is very regular, then they are the integral, the mean curvature. I mean, take all the curvature, take the then you multiply, instead of multiplying, if you multiply all the curvature, you have the Gauss curvature. If you just sum up the mean curvature, Then you take the multiplication of 2 with 2 and you sum up, then this is the second curvature. Integrate this, you have one of these, then you integrate.
Okay, thank you very much.
Any other questions? Do we have any questions from our online participants? Okay, then let's thank Paolo again. Thank you very much for this great talk. With that, we conclude today's TSVP talk. Thank you very much for joining.